Welcome to AI Frontiers, where we explore the most exciting developments in artificial intelligence research. Today we're diving into breakthrough robotics research from Computer Science Robotics, featuring revolutionary advances published on July 11, 2025. These papers showcase fundamental breakthroughs in robotic perception and learning, from sparse-view reconstruction to whole-body control, demonstrating how researchers are bridging simulation and reality with AI. We'll explore 10 groundbreaking papers that are reshaping the field of robotics. Picture this. A robot delicately hands you a cup of coffee, its movements so fluid and natural that you forget you're interacting with a machine. But here's the remarkable part. That robot learned to perform perfect handovers without any physical training whatsoever. Instead, it mastered this complex manipulation task from just a few photographs of humans passing objects to each other. No thousands of hours of practice were required, no extensive real-world training data. This isn't science fiction anymore. It's cutting-edge reality emerging from robotics laboratories around the world, where researchers are solving problems that seemed impossible just a few years ago. What makes today's collection particularly fascinating is how these 10 papers, all published on the same day, collectively paint a picture of a field in transformation. These aren't just incremental improvements to existing technology. They represent fundamental breakthroughs that could reshape how robots perceive, learn, and interact with our world. From self-repairing spacecraft that can fix themselves in the vacuum of space to humanoid robots that walk with human-like grace, we're witnessing the moment when silicon truly meets the physical world. The convergence of advanced computer vision, sophisticated learning algorithms, and robust control systems is creating entirely new possibilities for robotic intelligence. To understand the significance of these breakthroughs, imagine robotics research as a vast ecosystem, like a rainforest where different species have evolved specialized abilities to thrive in their particular niches. Computer science robotics sits at the heart of this ecosystem, combining computational methods, artificial intelligence, and engineering principles to create the software brains that make robots intelligent. This interdisciplinary field draws from multiple streams of knowledge. Computer vision provides the eyes, helping robots see and understand their surroundings with increasing sophistication. Machine learning serves as the adaptive nervous system, allowing robots to improve through experience. Control theory acts like the cerebellum, ensuring precise coordination. Human-computer interaction forms the social layer, enabling natural collaboration between humans and machines. The first major research theme demonstrates the integration of advanced visual perception with robotic manipulation. Wu and colleagues showcase how robots can learn complex manipulation skills by studying photographs rather than requiring extensive real-world training data. This approach bridges the gap between what robots can see and what they can do, like teaching a painter not just to observe a landscape, but to understand how to recreate it with brushstrokes. Using Gaussian Splatting reconstruction, their work on human-to-robot handovers represents a novel approach where robots learn manipulation policies directly from visual observations. The technique creates realistic three-dimensional scene reconstructions that serve as perfect training grounds for robotic policies, eliminating the need for thousands of hours of physical practice. A second prominent theme centers on robust multi-sensor fusion frameworks that combine information from diverse sensor modalities to create more reliable robotic systems. This is like creating a symphony orchestra, where different instruments, LiDAR, cameras, GPS, and inertial sensors must play together harmoniously, even when some musicians are having an off day. Several papers tackle the challenge of maintaining system reliability under challenging conditions. The comprehensive benchmark for sensor fusion ground slam demonstrates how researchers are systematically evaluating the performance of different sensor combinations under stress conditions, much like testing an orchestra by having them perform in a thunderstorm. These frameworks ensure robots can maintain robust performance even when individual sensors fail or provide degraded information. The third theme revolves around whole-body control systems that represent a fundamental shift from traditional robotic control approaches. Instead of treating robot control like a puppet show where different parts are controlled independently, these new approaches are more like teaching a dancer, where every movement flows naturally from the integration of multiple body parts working in harmony. The papers demonstrate sophisticated methods for unified control that can simultaneously manage walking, arm movements, and end effector positioning. Multi-critic learning architectures effectively resolve the inherent conflicts between locomotion and manipulation objectives, allowing robots to exhibit emergent behaviors where the robot's base actively assists arm movements, creating more natural and capable robotic behavior. The research presents several groundbreaking results that sound almost magical but are happening in laboratories right now. One of the most surprising findings shows that robots can learn effective manipulation policies solely from RGB images without requiring any real robot training data or physical demonstrations. Multi-critic systems demonstrate the ability to balance competing objectives naturally, with robots exhibiting emergent behaviors that surprise even their creators. Adversarial training creates robust motion policies that can handle real-world perturbations effectively, like having a sparring partner who constantly finds new ways to challenge the system. Spacecraft control systems achieve superior fault tolerance using advanced learning algorithms, crucial for missions where system failures can have catastrophic consequences. These findings collectively suggest we're approaching a threshold where robotic systems might begin to surprise us with capabilities that even their creators hadn't anticipated. Today's paper of the day comes from Wu and colleagues, whose work on human-to-robot handovers through sparse-view Gaussian splatting represents a fundamental shift in robot learning approaches. What makes this research particularly compelling is how it elegantly solves a problem that has plagued robotics researchers for decades: the enormous amount of training data typically required to teach robots even simple manipulation tasks. The team recognized that if humans can learn complex manipulation skills by watching others, robots should be able to do the same. Their breakthrough came through innovative application of Gaussian splatting, a technique originally developed for computer graphics that creates incredibly realistic three-dimensional scene reconstructions from just a few camera viewpoints. The system works by reconstructing human-to-robot handover scenes using sparse-view Gaussian splatting, creating detailed reconstructions that serve as perfect training grounds for robotic policies. The technical elegance of their approach lies in its simplicity and effectiveness. Gaussian splatting creates detailed three-dimensional reconstructions from few viewpoints, originally developed for computer graphics applications. The technique generates synthetic training data that is indistinguishable from reality, effectively bridging the visual domain gap between simulation and real-world conditions. The camera mounted on the robot gripper creates a direct mapping between visual observations and robot actions, enabling the system to generate synthetic training demonstrations that transfer seamlessly to real robots. This innovation enables learning from natural human demonstrations captured in everyday settings, without requiring specialized equipment or controlled laboratory conditions. The approach transforms how we think about robot learning, moving from expensive, time-consuming physical training to efficient learning from visual observations. The implications of this work extend far beyond handovers, potentially transforming robot learning paradigms across numerous applications. The approach dramatically reduces the cost and complexity of robot training while improving the realism of synthetic training data. It opens possibilities for learning from historical video footage, essentially allowing robots to learn from the collective experience of human civilization. The research demonstrates how advanced computer vision techniques can serve as powerful tools for translating between different domains and modalities, enabling robots to understand and interact with the world in more human-like ways. This could enable more rapid development and deployment of robotic systems for tasks ranging from household assistance to industrial automation. The success suggests we're entering a new era where the boundaries between simulation and reality are becoming increasingly blurred, potentially accelerating robot deployment across applications. Looking toward the horizon, these breakthroughs paint a picture of a future that's both exciting and transformative. We're approaching a threshold where robots won't just be tools following pre-programmed instructions, but intelligent agents that can understand context, adapt to unexpected situations, and collaborate naturally with humans. The integration of vision-language models with robotic planning suggests robots that can understand and respond to natural language instructions contextually. Imagine telling a household robot that the living room looks messy and having it understand not just the words, but the implicit knowledge about what constitutes messiness and how to address it. Advances in simulation to reality transfer point towards robots that can learn new skills overnight by training and simulation, then seamlessly apply those skills in the real world. General-purpose robotic platforms will adapt their behavior dynamically based on situational requirements, much like humans do instinctively. These robots will become true partners in human endeavors, augmenting our capabilities rather than simply replacing human labor. The research we've explored today represents far more than incremental improvements to existing technology. These papers showcase fundamental breakthroughs that are reshaping our understanding of what's possible when artificial intelligence meets the physical world. Wu and colleagues, along with other researchers, demonstrate revolutionary capabilities that address fundamental challenges limiting real-world robotic deployment. The convergence of advanced perception, sophisticated learning algorithms, and robust control systems creates possibilities that seemed like pure science fiction just years ago. From robots learning complex manipulation skills by studying photographs to spacecraft, maintaining control under fault conditions using advanced learning algorithms, we're witnessing the emergence of truly intelligent robotic systems. These advances address the ability to learn from sparse visual observations, handle multiple competing objectives, and maintain robust performance under challenging conditions, capabilities essential for robots operating in the messy, unpredictable real world while creating natural human-robot collaboration. This content was synthesized using Claude-Sonnet-4 from Anthropic, with text-to-speech synthesis powered by Deepgram and image generation through Google AI. Human expert review was conducted for accuracy, though some oversights may exist, and references are provided for verification. The research papers discussed are available on the archive preprint server, and we encourage listeners to explore the original sources for complete technical details. Our AI synthesis process aims to make complex research accessible while maintaining scientific accuracy, though we recommend consulting the original papers for comprehensive understanding of methodologies and results. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Subscribe for daily AI research insights and explore breakthrough papers across all fields. Get expert analysis of emerging technologies and join our community of AI enthusiasts. Never miss the next breakthrough. Subscribe now for daily updates. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by the archive preprint server.